I'm going to talk a bit about, sort of take a step back from the sort of new wave of the small satellite missions. You saw some CubeSats in there. I'm going to talk about a more traditional NASA mission, and more specifically about the Global Precipitation Measurement Mission. And since we are in the College of Engineering here, we're an engineering society, specifically looking at remote sensing, I'm going to talk about connecting the science of GPM to the engineering implementation of GPM. Try to connect those together, much as Chris connected the science goals of Cygnus to the engineering details of the implementation of Cygnus. And along the way, I'm going to point out engineering gone awry, just because, you know, a lot of the forefront of engineering education amongst the students here is learn by doing, and really often what we want you to do is to, frankly, to fail as you're doing, because you learn more, and because we get to laugh at you when you fail. No, and that's not the real reason. It's because you learn more when you find the mistakes. And I'm going to point out, I'm going to be quite frank about the mistakes of some of the GPM instruments, and how we've gone about figuring out what's going on, what's gone wrong, and how to fix that. So I'll point out some of that along the way. So I'll talk about GPM, but you know, as with all things, as we move forward, we want to talk first of all about what's already been done. So before I talk about GPM, which is the present of NASA and JAXA, I should note that it's a major partnership between Japanese and American space agencies. So GPM is our present Global Precipitation Measurement Mission. It follows directly upon the past mission, which is the Tropical Rainfall Measurement Mission. So I'll talk briefly about TRMM, and that will lead into what GPM wanted to do beyond what TRMM had already done, so GPM goals. And from there, I'll talk about the GPM microwave imager, which was mentioned earlier, this GMI instrument, what GPM and GMI have done that went beyond what TRMM and TMI did in terms of engineering and calibration, and radiometer intercalibration. Steve Rising mentioned that, brought that up, and so I'll just briefly talk about what we're doing with that within the GPM constellation. And along the way, I'll tell you about all the issues that have come up with GMI, as well as the rest of the instruments in the constellation that we've had to try to fix in order to accomplish the intercalibration, and wrap it up with sort of where we're going next to try to get better precipitation data with the next follow-on mission. So let's talk about TRMM and GPM science, how the two are related, how GPM is meant to go beyond TRMM, and what that specifically meant in terms of how the mission overall, as well as the instruments within GPM, were designed to improve upon TRMM. So TRMM, Tropical Rainfall Measurement Mission, launched in 1997 and lasted until 2015. That's actually well beyond its intended original lifespan, and part of the reason why they kept it going, and it actually involved boosting the orbit in ways they never expected to do, is because the follow-on mission, GPM, had some lags in funding. So it was supposed to come very closely in on the heels of TRMM, but it was delayed, so TRMM was extended. But the main goal of TRMM, the Tropical Rainfall Measurement Mission, as the name implies, is measuring tropical rainfall, which is responsible for about 3/4 of the energy driving the global weather patterns through the precipitation, latent heating. So TRMM goals specifically, from a scientific top-level standpoint, were to characterize the amount and distribution of tropical rainfall, to test and improve satellite precipitation estimate techniques. So this is 1997. Precipitation from satellite was by no means new. But TRMM introduced some new channels within the microwave imager. It also introduced the coupling of both a radar and a microwave imager on the exact same platform, making co-located measurements. And so there were questions to be answered about how those two play together. And so there were some new things to explore there. And in particular, TRMM consisted of, as does GPM, both ground and airborne assets, but I'll focus primarily on the satellite assets. So TRMM had a microwave imager, TMI. It also had a precipitation radar, PR. It also had a vis-IR sensor, which GPM didn't pick up on the core constellation, on the core spacecraft itself, but there are a lot of other vis-IR sensors that we use data within PMM and GPM. And a lighting sensor, as well as Earth's radiation balance sensor. So that was TRMM. And the goal for GPM, which the core GPM satellite launched in 2014, so in other words, it's quite a bit after the tube trim. And originally, GPM was supposed to launch more like 2000. More like 2005. It was delayed by almost 10 years. But so it had similar goals to trim, but expanded. As you might guess, one of the ways it expanded, it was not just tropical, but it's now global. So that's one of the ways. So the improvements from GPM to trim were extended to a global, not just tropical mission. Cover all phases of precipitation. So the other thing you'll notice in the names is it was a tropical rainfall measurement mission. So tropics to global precipitation, global, and precipitation, not just rainfall. So we wanted not just rain, but we wanted hail, we wanted snow, we wanted graupel, we wanted all phases of precipitation. We of course wanted to improve the accuracy, the dynamic range of the precipitation products, improve our understanding of the link between precipitation and climate, and improve our general water cycle knowledge through the whole precipitation, cloud formation, evaporation, watershed cycle. Improve our ability to observe severe weather phenomena, and also improve our ability to measure brain microphysics. And so the way we take all these improvements for GPM compared to trim and flow them down into the instrumentation is basically, I'll give a brief summary of that in the next couple of slides, but the primary ways are improving the two primary assets on the GPM satellite, which are the GPM microwave imager, GMI, which Steve introduced earlier, but also taking the precipitation radar from trim and adding on a second frequency set to that to make it a dual frequency precipitation radar to get additional microphysics. I'm not going to talk about the DPR today. Actually, there's going to be a seminar in early December on the expert from JAXA on the DPR. So you hear all about that if you come back to that talk. So I'll leave that aside. And I'll talk about what I worked on, which is GMI. And so let's just talk about some of those top level goals, all phases of precipitation, improved microphysics, improved dynamics, severe storms, climate, and talk about what that means in terms of what you do with the mission and how you run the mission to make GPM meet all those goals relative to trim. So, global versus tropical, what was the main change there? That one was pretty straightforward. Trim, being a tropical mission, much like Cygnus is a tropical mission, had a relatively low inclination orbit. And so the trim orbit was inclined at 35 degrees, so mainly focused on the tropics. The GPM orbit shifted that up to a 65-degree orbit. And why not do a polar orbit? I'll touch on that, but it actually relates to Charlie Powell's question about intercalibration is one answer to that. But anyway, I'll talk a little bit more on that in the future, a couple slides from now. So rain versus precipitation. So as I mentioned, now don't want to just measure rain, you want to measure snow, hail, graupel, everything that precipitates, all hydrometeors in all phases. And so basically, the main implication of that is on the microwave imager side, which again is what I'm going to focus on, is to add high frequencies to the radiometer channel sets. Because at the high frequencies, what we can do is we can pick up quite strongly the scattering signature of snow. If we go up towards those 183 gigahertz channels, which traditionally, as we saw in the previous talk, are for water vapor, but we can also pick up scattering off the snow. And actually at the 89 gigahertz, which the channel set we've included for, and trim had an 89 gigahertz, you could pick up hail at 89, but we pushed that out even into the millimeter wave up towards 180, getting close to 200 gigahertz, we pick up the snow as well. So that's the main implication for changes to GPM, is to add those high frequency channels. And to improve the calibration in order to get better accuracy and better stability, and also to do climate studies, we need to do more stable, more calibratable instruments, and also tie GPM measurements to measurements of the past as well as measurements from other radiometers by intercalibrating a number of different data sets to string them all together to get a very long data set going all the way back from, in GPM's case, from the first launch of the SSMI series all the way through GMI, as I'll show you near the end of the presentation. So we've got a number of different upgrades that basically boil down to changing and expanding our channel set on our microwave imager, improving the calibration, and improving the stability of the radiometer set so that we can better intercalibrate for longer data records that are more consistent from radiometer to radiometer. Okay, so that's the first set of implications. Further on, I mentioned the desire to look at storm structure, severe storms, severe weather, and look at improved severe weather monitoring and fold that into better prediction, which basically comes down to improving resolution. Specifically, what I'm talking about here is temporal resolution, because you want to check the evolution of these systems. And so it also is spatial resolution, which basically sets the size of the imager, but it's also temporal resolution. So if you look at the sort of goals and revisit time for GPM, the goal was to get to about 3-hour revisit time, and if you think about what was already shown by the orbital overpasses that Steve Rising was showing, and plus what Russ showed in Cygnus, if you just have a single instrument, you're going to have more like a 3-day revisit time. So if you want 3-hour revisit time, you need to go more like what Cygnus did, is fly more than one radiometer. Now GPM only had funding to fly one radiometer, that's GMI, so that meant you had to get agreements with a bunch of other radiometers to form a constellation of radiometers that you can then intercalibrate, which once more flow back into a requirement to make sure your radiometers very highly quality calibration, so it can be intercalibrated with all the rest of the constellation. And then there was the rain microphysics, and that's actually one of the main things that I'm sure that our guest from Jackson will talk about in a few weeks, which pushed them to a dual frequency radar implementation, where you can use the frequency difference between the two radar channel sets to infer raindrop size distributions. And so that's basically the top level in terms of instrument implementations. The changes going from GPM from TRMM based upon the stated science goals. Okay. So as I mentioned, in order to get the temporal resolution and also to put together the long time series to go look at climate studies, the GPM was always intended from the get-go not just to operate on its own, because as I said, we only had enough funding to fly the one radiometer, but we knew we would want to fly it in concert and match it up with all the other available radiometers. Some of them that have already been mentioned, JPSS, AMSR 2, and international collaborations with ISRO and CNES, with Megatopeak, with the NOAA constellation of radiometers. We knew we would have to intercalibrate with all of these, so again that pushed us towards making sure GMI was highly calibratable. And so some of the changes we made with GMI were very highly focused on being able to better calibrate and better understand the stability of the calibration for our GMI instrument so that we could better intercalibrate to the rest of the radiometers, of which there are several within the constellation, so that we can get that 3-hour revisit time. And it also helps us in order to stitch together that longer climate record so that you don't confuse an instrument drift or a climate drift. Basically is what it comes down to. So this is a depiction of the GPM Core Satellite itself. So up top, this is the GMI, the microwave imager here. It's a conically scanning microwave radiometer. So if you imagine this satellite flying along in this direction, this instrument up top of the microwave radiometer is rotating, it's spinning. So as it moves along, that rotating reflector scans out footprints across the swath as it moves in the forward direction, scanning off a fairly broad, several 100-kilometer swath width as it sweeps along. And then sitting at the bottom of the instrument is that dual frequency radar system with co-located measurements underneath that line up with the radiometer measurements to get us some more insight into the rain microphysics, as well as giving us a vertical resolution because it's a ranging Doppler radar system. And so that's the basic core constellation, and then we add to that several other radiometers to flesh out the temporal resolution piece of the puzzle to get the severe storm evolution piece that we wanted to add with GPM. And so I want to go into a little bit into some of the GMI innovations. Again, primarily focused on calibration, and that'll lead into what I said before, which is being honest about the mistakes that we made with not just GMI, but past radiometers, which basically kept a number of us employed in figuring out how to fix those mistakes so that we can get them intercalibrated so they will all be consistent. In an ideal world, if two radiometers are measuring the same location at the same time, they would give you the exact same observation. The reality is they never do. You need to figure out why they don't. It's basically a mystery novel that you need to look at the clues and figure out why don't they agree. And if you can figure it out, can you correct it? And if you can't correct it, what are you going to do about it so that you can get a consistent precipitation record out of it for the case of the GPM mission. So, so let's just talk about very, very briefly hydrometeor observations in general. The way we do these hydrometeor, so again, we're not just looking for rain, we're looking for snow and hail. The way we do these measurements is basically two classes. Over ocean, what we do is we look for the emission of the rain, primarily is what we're going to get out of emission, over the cold ocean background. Okay, and basically, I won't spend a lot of time on that, but it's basically the relation. We can have a relationship for a given frequency between the rain rate and the brightness temperature, which is our basic fundamental measurement. We're always measuring brightness temperatures in these radiometers and estimate how bright they are relative to their physical temperature. So as the rain rate increases, its brightness temperature increases. And there's some frequency and polarization dependence of that allows us to tease apart some of the lower level details about raindrop size distributions. And some frequencies are more sensitive to lower rain rates, some to higher rain rates, so we want a range of frequencies and polarizations within our channel set. So that's what we do over land for rain, over ocean for rain. So over land, what we look for is not this increase in brightness temperature from emission, but what we look for over land, because land tends to be relatively warm compared to ocean, which is relatively cold. Over the warm land, what we look for is precipitation scattering, and that's seen as a decrease in the brightness temperature from that scattering. And I won't go into the details, but for scattering, what you want are wavelengths that are of order the size of the scatterer. And so the scatterers in the raindrop to hail to snow are in the centimeters to millimeter wave size scatterers. So we want centimeter to millimeter wavelength radiation to measure that. So that's what I mentioned in the GPM. When we wanted to pick up that snow, we needed to push it to higher frequency, smaller wavelengths so we can pick up the smaller snow particles. And we do that by a scattering signature. So here's an example of an image at 89 gigahertz, which is a channel set that has been around for quite a long while. This is vertically polarized. But you can see this is a TMI, one orbit of TMI, and you can see that in general over the ocean, the 89 gigahertz brightness temperatures are hanging out fairly modest 260 kelvins or so. But you can see over this swath over land, you can see it dips down quite cold, all the way down to about 160 kelvins. That's a storm system. You've got a lot of hail in that particular system, deep convection. That's decreasing the brightness temperature due to the scattering off that hail. And so that's how we pick it up. So in all these games, all these precipitation measurements, what we're doing is we're connecting the brightness temperature that we observe to the amount of precipitation that we're seeing, either as a decrease in brightness temperature for the scattering signature over land, or as an increase in brightness temperature from the emission over ocean. So we're always connecting brightness temperatures to precipitation amounts. And the way we do that is we need to calibrate our on-orbit measurements to some standard of a known brightness temperature. So what vast majority of these radiometers do is while they're on board, they make observations of two sources, one cold and one warm, as just a normal part of their operation. So usually what they use, and Steve Rising mentioned how they do this on his radiometer, they make a measurement of the cosmic background at 2.7 Kelvin, that's your cold point. And so whenever you make your radiometer measurement of digital counts, is typically measured at cold microwave background, and you can tie that number of counts off of your detector to 2.7 kelvins. And then you make a second point at some warm source, which usually what you do is you fly some microwave absorber that you look at some portion of your scan, and you measure the temperature of that microwave absorber, and it'll typically be around 290 Kelvin. That gives you a warm point that you can convert from counts to brightness temperature at 290 Kelvin. And what you do is that for everything in between, which is basically all your Earth observations, depending upon whether it's precipitation over ocean or over land, it's going to lie somewhere in between. So you linearly interpolate the counts to brightness temperature using those two references as your standards to do the conversion. So that's basically what we call a two-point calibration. And that's what everything hinges on in terms of changing your brightness temperature into a precipitation estimate, is that two-point calibration. Okay? So that brings us to known issues with radiometers in the past, and then the discussion of what we tried to do to fix those issues for radiometers like GMI, as well as the radiometers moving into the future. So basically, I'm not going to go through all the details of all these, but basically what's happened is that someone that's a scientist, an end user, will take a look at the data after this thing's on orbit, and they'll see data that don't follow any sort of normal, recognizable physical pattern. And sometimes they'll say, oh, I've discovered some new geophysics. But actually what's happening is there's an engineering problem. And obviously, we want to avoid that. So one example of that, antenna pointing offset problems. There's actually a fairly well-known case in the calibration world of a particular instrument that had 89 gigahertz, two different receivers, two different feed horns, one for V pole, one for H pole, and they were pointed slightly off. And so someone observed a V minus H difference in the on-orbit observations, and they said, here's a source of new geophysics. There's this V-H polarization difference. That must be due to ice scattering from precipitation, and I can use that to retrieve ice precipitation. But in fact, what it really was is the V and H weren't actually looking at the exact same location. It was an engineering problem, not a geophysics problem. So they then later had to retract that statement. We went back and discovered the offset by studying the fact that this new radiometer sees this VH difference, but no other radiometer sees that same VH difference. And they're looking at the same scene, they should see the same geophysics, but they don't. So that's your first hint, this isn't geophysics. If it were geophysics, the Earth doesn't care if it's GMI or if it's TRMM, or if it's Steve Rising's instrument. If it's geophysics, they should all see it. It should be all the same, it should all work the same. But if only one of the three of them sees it, it's sort of like a voting rule. If one sees it and the other two don't, then you suspect there's something wrong with the one that sees it. And so you dig into it deeper. So you develop these clues and you dig into them. And so that's one example, the type of engineering artifact that showed up in data that was mistaken for a geophysical artifact, and it was actually an antenna pointing offset. So that's one example. And Mr. Reflectors have been a number of instruments, TMI included, where the main reflector, that big spinning dish up top, is supposed to be a highly reflective surface, hence the name reflector. It isn't always as highly reflective as we would hope. And in TMI's case, as well as some of the other instruments, basically what had happened is that reflector had been ablated by atomic oxygen in a low Earth orbit that degraded the reflective coating, so it was partially emissive. And so people looked at this, and initially what they saw was day-night, and an ascending pass and descending pass difference. That initially they thought, well, maybe there's some diurnal, because some of these instruments were sun synchronous. So you had it would fly overhead one particular location at 6 a.m. and then fly over the same location again at 6 p.m. You would look at the 6 a.m. observation and the 6 p.m. observation, you would see the significant difference. And so initially the scientists thought, well, there's some diurnal effect. There's a difference between 6 a.m. precipitation and 6 p.m. precipitation. But again, when you looked at it from a different radiometer, it didn't see that. What it turned out was, it wasn't a geophysics diurnal thing at all. What it was is that the solar illumination on that main reflector was heating it differently at 6 a.m. than it was at 6 p.m. Okay, so you're getting these clues that it's something engineering related. Basically, the reflector was hotter at one time of day because of the solar illumination than it was at the other. And because it was partially emissive, it was leaking radiation, had nothing to do with geophysics into your observation. And you had to basically correct that out before you can unambiguously determine what the geophysics was. So that's another example. There have been other examples, intrusions in the cold sky review. So you had that cold sky reflector looking at that cold sky, but it isn't always purely looking at cold sky. Sometimes it's intercepting part of the spacecraft. Sometimes the moon gets into that part of the field of view, sometimes the sun, so you had to watch for that as well. So with all these issues in the data, we knew about these when we designed the GMM, so we decided to try to handle these to improve GMI calibration by eliminating as many of these as we possibly could. So I'll briefly describe how we did that and then show you how we also messed up along the way. So just, happens to the best of us. So emissive reflector, one way of doing that is we did a lot of testing of the coatings so that it wouldn't degrade on launch, so that it stayed nice and highly reflective. Sunlight in the hot load is another common problem with these microwave radiometers. Certain solar geometries, the sun could illuminate the hot load that was supposed to be this well-known temperature stable load that you would use as that reference for the hot point in your 2-point cal. But if the sunlight gets on there, it'll differentially heat up half of it, but not the other half. So we did some updates to eliminate that by basically shielding the hot load. Intrusion in the cold sky view, we shaped the cold sky reflector and shifted some of the spacecraft structure outside of this cold sky view to eliminate that. Antenna pointing offsets, and we basically did a lot of pre-launch measurements to make sure that we understood well the alignment of the feeder point with respect to the main reflector, and we did a lot of post-launch analysis to make sure that if there were any misalignments, we could correct for them. And I'll show you an example of that and give you a warning of how to do that correctly and how some folks did that incorrectly and actually introduced more problems than they solved. I'm not going to go over the pre-launch characterization inaccuracies, but I'll just point out some of the highlights of some of the changes we made. So that's GMI once it was integrated at Ball Aerospace before being put on the GPM Core Constellation. Some of the actually, I'll just zoom in on the calibration subsystem. So here's the hot load. And normally on these radiometers before GMI, the hot load would just be sort of sitting out in space, and that's what allowed the sunlight to get directly on the hot load. This one has been shrouded all the way around so it can't leak in from the side, and it also has this ring around it with these lips on the ring so that it also can't leak in and bounce off the deck and bounce up into the hot load. So we did a lot of work to isolate that. Typically these cold sky reflectors are just simple parabolic reflectors. This one is not even close to being a parabolic reflector. You can tell by the shape, it's quite a funky shape. That was designed for you antenna geeks. That's basically, we designed that. It's an elliptical reflector. The elliptical shape gives it a beam waist that narrows the beam just as it's going past the spacecraft structure to avoid interference from the spacecraft into the cold sky review. Little things like that just to improve calibration stability. One other thing we did with GMI is we added noise diodes. These are an independent reference that injects some warm noise into the observations. It gives you not just 2 points for calibration, cold and warm, but now you have actually 4, because you can do cold plus noise, and warm plus noise. This allows you to not just get a linear relationship to convert from counts to brightness temperature, but you can actually get a nonlinear one and remove nonlinearity. I'll show you why that's important in a minute. And you can also do 2 point 2 different ways. So if your cold sky is in question, you can do warm and warm plus noise for 2 points. Or if your warm load's in question, you can do cold and cold plus noise for your 2 points. So you basically get redundancy to check everything and make sure it's all stable. Okay. And so, and I think we're running a little bit low on time, but this was just another example of an offset. This is WinSat data that I took as part of the GPM Constellation. And what these are cold and warm, and their differences as a function of the scan position between the WinSat observations and the model of the Windset observations. And ideally, as a function of scan position, there would be zero bias. So it would be flat all the way across, but you can see it's tilted. And that's because the feed horns for each of these Windset channels are offset just a little bit. So there's a persistent roll that shifts all the biases. And the Windset observation is a function of scan position. So here's a warning that you need to think about some of the physics of what's going on here. What some of the colleagues did at, where's Charlie, plug your ears, NOAA. What some of our colleagues at NOAA did is they saw this bias, and what they did is they said, okay, I'm going to subtract off, as a function of scan position, 0.2 kelvins at this end, and minus 0.4 kelvins at that end, based upon these over ocean measurements, and call it good. So statistically over ocean they were good, but over land, look at the biases you can measure against this reference are significantly different. So they fixed it over ocean and made it worse over land, because they didn't understand that this is not a brightness temperature issue, this is an alignment of the feed horn issue. So this is not inherently a brightness temperature issue, it's the fact that because the feed horn is misaligned, your incidence angle at which you're observing the Earth is not what you think it is. It's just shifted slightly, so your brightness temperature is shifted slightly. You don't fix it by fixing the brightness temperature, you fix it by fixing the incidence angle. So that's how you know. You got to think about the root causes and chase down all the little details and get a bunch of different looks at it. One last thing, and then I'm going to just open it up for questions. GMI by no means was a perfect instrument. This is an example, much like the Windset data I just showed you at cold and warm end, as a function of scan position of the biases with respect to model of the GMI measurements at various channels. And you can see it's smaller than the Windset biases, but there's significant biases here, a low bias here, and a high bias here. That shows up at both cold and warm ends. And if you look at the details, there's also this sort of oscillation in the brightness temperature bias. And this is actually an advertisement for working in a large set of engineers and sharing all your results with a broad set of capabilities. So the calibration engineer at Ball did analysis of this FFT analysis and determined the frequency at which these oscillations occur. And he said, hey, look at this to his fellow engineer. I got these oscillations showing up at these particular scan positions plus these oscillations that occur at this particular frequency. And he said, well, you know, that just so happens to match the positions at which we put these magnetic launch locks that held the main reflector down on the deck before it was deployed. And those frequencies, the oscillations of the frequencies just so happens to measure the spin rate of the instrument itself going past these magnetic launch locks. And so the two of them were able to put together. What's happening is as the receiver goes by these magnetic devices that were holding down the main reflector pre-deployment, it's inducing a current in the bias circuitry of the radiometer that's throwing off their gain, which is throwing off their calibration. Okay, so it had nothing to do with brightness temperatures. So the fix is not to subtract all this off from it. The fix is to realize that at these particular scan positions you biased into the magnetic effect and fix it at the root cause. And that basically, that conversation came about because they shared cubicles right next to each other and just happened to be talking about it. And one recognized that the frequency matched his analysis of the spin rate of the instrument plus the location of the magnetic locks. So they put two and two together and said, well, that's the root cause, and now we know how to fix it. So, at any rate, one last slide and I'm done. So, Steve Rising mentioned this. This double difference method is the way that we intercalibrate our radiometers. And so here's a big suite of radiometer double differences, a number of instruments, trim TMI, answer 2, SSMIS, SSMI, Windset with respect to GMI for various channel sets. There's nothing of particular note here other than that, you know, these actually, I'm really quite amazed at the CubeSat. They're all within the same range, these double differences on his CubeSat mission as these full-blown missions, as he already noted. There are a couple of exceptions. Answer 2, if you look at the 18 gigahertz V and the 18H, they sort of stand out as the high. They're 4 kelvins off with respect to GMI and with respect to several of the other instruments. And this actually turns out to be a nonlinearity problem. They miscalculated the nonlinearity in that particular channel set. And so if they had those noise diodes on it to measure the nonlinearity, they'd be able to fix that. So they didn't, so we're having to fix that in the post-processing. So that's basically in a nutshell, just some idea of how we took science requirements, GPM, and flowed them down to engineering implementation, and some of the issues we found along the way, and some of the idea of how we go about correcting those. So with that, I'll wrap it up. If you have any